All right, let's talk about how machines are learning to do something that we find so natural, we don't even think about it. Seeing. We're going to dive deep into the world of computer vision. To really wrap your head around the scale here, just think about this. Every single minute of every single day, we're uploading an insane amount of visual stuff. We're talking over 100,000 photos to Facebook, about 20 hours of brand new video to YouTube every minute. It's this absolute digital deluge, and it raises a really big question. What do we do with all of it? And that's exactly where this field comes in. Computer vision. It's basically the science of teaching computers how to see. It's about getting a machine to look at an image or a video and not just see a bunch of colored dots, but to actually understand what's in it, to see a cat, a car, a person walking down the street. So here's the game plan for today. First, we're going to tackle that deluge of data. Then we'll look at how you can possibly search through a billion photos. From there, we'll get into how we teach pixels about people and objects. Then we'll see it all in action, in a self-driving car. And finally, we're going to ask a really big question. What is seeing really for? Okay, let's start with that first massive challenge, just grappling with this ocean of pixels that we are creating all the time. See, the really crucial thing to get here is that having billions of photos is completely useless if you can't do anything with them. The challenge isn't about storage anymore. Not really. It's about making it useful. How do you find the one image you're actually looking for? How does a computer learn the difference between a picture of a dog and a donut? And, maybe most importantly, how do you use that understanding to actually take action in the real world? Which brings us right to our first set of solutions. How do you find that digital needle in a haystack? How on earth can you search through a billion photos almost instantly? Well, the answer is it's actually pretty brilliant. Instead of trying to compare these massive, clunky image files directly, which would be incredibly slow, these systems create a kind of compact fingerprint for every single image, a binary code. Think of it like a souped-up, super-powered digital card catalog. You're not slowly wandering through the entire library, you're just zipping through the cards to find what you need in a flash. So how do we teach a machine to make those smart little fingerprints? Turns out there are two main ways to go. On one hand, you have supervised methods. That's where we give the machine a head start. Humans go in and label tons of data, basically saying, hey, these pictures of cats are similar. The machine learns from our examples. But then you have unsupervised methods, where you just dump all the data in and let the machine figure it out for itself. It finds the patterns, it discovers what's similar, all on its own. Okay, so searching is one huge hurdle, but actually understanding what's going on inside an image, that's the next level. And we're going to start with one of the most complex subjects out there, us, people. It's not enough to find a photo with a person in it. We want the machine to get what that person is doing. And a giant piece of that puzzle is something called pose estimation. It's the ability to look at a 2D image and figure out where someone's head, arms, and legs are in three-dimensional space. It sounds simple, but it's incredibly hard, and it's the key to unlocking everything from new video games to activity recognition. So how do you actually do it? Well, you break the problem way, way down. First, you treat every single pixel like it's taking a little quiz. The question is, what body part do you think you belong to? To teach it the answers, you generate hundreds of thousands of fake, but super realistic images of people in all sorts of poses. You feed all that training data into a powerful engine, something called a randomized decision forest, which just gets really good at seeing the patterns. And the result? A system that can look at a new image and, in real time, make these incredibly fast, accurate guesses about where all the person's joints are in 3D. Now, of course, it's not magic. It's not foolproof. This tech is still learning, you know? Simple things that we do without thinking, like just crossing our arms, can totally throw the system for a loop. If the algorithm hasn't seen a very specific, weird pose in its training data, it can really struggle to make a good guess. And that just shows you the kinds of challenges that are still out there. And what's really cool is that these same ideas of breaking down a really tough visual problem, they apply to way more than just people. How do you teach a machine to recognize a specific 3D object, say a coffee mug or a car part, no matter what angle you're looking at it from? Well, it's a pretty neat multi-step process. First, the system uses cameras to build a 3D point cloud of the scene. It's like a digital cloud of dots. Then it looks for distinctive features in that cloud. You know, things like corners or edges or unique curves. Now here's the clever part. Each one of those features gets to vote on where it thinks the dead center of the object is. The system just looks for the spot that got the most votes, and boom, it aligns its own 3D model right on top of that cluster. And this image here shows you that whole pipeline in action. You start with that raw, kind of messy point cloud from the real world, you run it through that feature detection and the clever voting process, and what you get on the other side is a perfectly aligned 3D model. The machine has literally gone from seeing a cloud of digital static to identifying a specific object in physical space. It's incredible. Okay, so we've gone from searching images to understanding what's inside them. So now let's put it all together in what might be the ultimate test for computer vision in the real world: a self-driving car. A self-driving car doesn't just see with cameras. It's actually fusing data from a whole bunch of different senses to build this kind of superhuman picture of the world. It has stereo cameras, which give it depth perception like our eyes. It has LiDAR, which uses lasers to build a stunningly precise 3D map of everything around it. And then it has GPS and other sensors that tell it exactly where it is and which way it's pointed. And this right here, this is the whoa moment. On the left, you've got what we see, a normal highway scene. But on the right, that's what the car sees. It's not a picture. It's a constantly updating, millimeter-accurate 3D point cloud of its entire environment. Every other car, every guardrail, it's all just a collection of data points in space. Now, having this kind of incredible sensory data lets the car's vision system just lock on to critical details, like the markings on the road. It can spot them with incredible confidence, even when conditions are tough, like if the paint is faded, or it's dark, or the road is curving sharply. And that same level of perception lets the vehicle find and track all the other moving things around it, like the car right in front. This ability to see, to understand, and to predict what's happening in the world in real time, that is the absolute bedrock of how autonomous driving works. And that brings us to our last, and honestly, maybe the most profound point of all. The goal of all of this technology isn't just to build a perfect picture of the world. It's about doing something. It's about taking action. There's this fascinating little creature in the ocean called the sea squirt. When it's young, it has a simple brain and it swims around, looking for a good place to live. But once it finds a nice rock and attaches itself for good, it does something absolutely remarkable. It eats its own brain. Why? Because once it doesn't have to move anymore, it doesn't need a brain for perception. And that little sea squirt tells us something incredibly deep about the whole purpose of vision. It's this core idea called actionable information. The reason we see, the reason animals and machines see, isn't to create some perfect high-def copy of reality in our heads. The purpose is to grab just enough information from the world to make a decision and perform a task. Vision isn't for seeing's sake. Vision is for doing. Which leaves us with one final, pretty big thought. For all of human history, what we could do has been limited by what we could see and perceive. But now we are building machines that will soon see and understand the world in ways that we just can't. So if seeing is for doing, what new things will become possible? What will machines decide to do when they can finally see everything?